This is the 5th lab of this course. We're using our Rosemount 1056 again here, but this time we have a conductivity probe connected to it. What I'll do is I'll just turn this, and this is a 2 electrode probe. You can see, let's see if I can focus this. There we go. So in the middle there, you should be able to see, yeah, there you can see it pretty good now. One of the electrodes, and then the other electrode is going to be this outer surface here of our conductivity probe. So we're going to be working with this probe here. We're going to be taking some readings here. You can see right now it's reading in microsiemens per centimeter right there for our reading up top, and then also temperature, because temperature will affect conductivity as well. So what we're going to go ahead and do is enter some parameters in here from the lab. I'll just take you guys over to the in-person lab here. The setup here for part 2 here, we're going to be entering this information. I'm going to go ahead and enter this information into the 1056 Rosemount analyzer, and then we are going to zero it with the electrode, or the sensor, the conductivity sensor, in air, following the procedure on page 82 of the manual. So we're going to go ahead and do that, and then after that we'll confirm that it's reading correctly with a sample here. We've got a sample of a known amount of microsiemens per centimeter. All right, so following the procedure in the manual, to enter in these parameters, we need to click the menu button and go down to Program, press Enter, and then go down to Measurement, press Enter. We only have the one sensor hooked up, so sensor 1. And here's all the parameters we need to enter. So we need to have the sensor type is 2 electrode. We have the type of 2 electrode. We need to have the cell K value. It needs to be 1 if missing, or as stated on probe label. So if we have a look here, I've got a probe here with a probe label on it, and you can see the cell constants right there, 0.98400, whereas this other probe over here, you can see it's missing its tag, so we would just enter in 1. But since we have the actual cell constant here, 0.9840, so 984, so we can change that. I'll press Enter here, and I'll change this to 0, 9, 8, 4, so there we have that entered now. And what else is on our list over here? Temp compensation needs to be slope. That was next on our list. And there, you can see it's set to slope already. The slope value should be 2% per degree C. RTD slope, 2% per degree C. We have that already set. And reference temperature, it says it should be 25 over there, and it's 25 here. Filter should be set for 2 seconds, and it's set for 2 seconds. Good, so all of that's set now. So now we're ready to do a calibration. Right now we're going to perform a calibration. You can see it's reading negative 0.03, so it's pretty close to reading 0. It should be reading pretty close to 0 when we have it exposed to air like we do right now. You can see the probe isn't wet, hasn't been dipped in any solution or anything yet. But we're going to 0 it, so I'll press the menu button again. We'll go to Calibrate this time, press Enter, and sensor 1, conductivity. We don't want to do the temperature, conductivity, and we're going to do a 0 cal. So I'll press Enter here. 0 must be in dry air, and we'll let it finish. You can see right up here, the reading up top now is right at 0.00 microsiemens. So we've completed our 0. I'm just going to exit out, pressing exit, and there, now you can see it's reading exactly 0. All right, so now that we've zeroed it in air, we're going to expose it to a solution of 2,000 microsiemens per centimeter here. And I've already actually dipped it in there. You can see I've kind of got a little bit of a reading over here. We're going to do that and see what it reads. So it should read close to 2,000. All right, so now that we have now that we've zeroed our sensor to air, I've got a buffer of a solution here. It's 2,000 microsiemens per centimeter. It's a calibration solution for this conductivity sensor. And so what I'm going to do is I'm going to just expose that, and we're going to check our reading there over on the 1056. And you can see it's pretty fast acting, and we're pretty close, pretty well 2,000 microsiemens per centimeter. Right about, just kind of shake this a little more and then let it sit. We'll take a reading 2017, so we're pretty close. I think we're going to skip the calibration here this time around. All right, so the next thing that we're doing here is we're taking a sample measurement here of deionized water. So if you're looking over here, you can see I've pulled the sensor probe out now. It's exposed to air, and the conductivity is lower. So now what I'm going to do is I'm going to expose this to deionized water here and see what we get for a reading. And it looks like for the deionized water, we're getting a reading of about, so let this stabilize. And what I'll do actually is I'll just drop this down into the sample. So there we've got a reading of about 5.3, about 5 to 6 microsiemens per centimeter. All right, so for our next reading that we need to take, we need to add salt to our deionized water. So this deionized water that we just took a reading on, we got about 5 microsiemens per centimeter. I'm now going to go and add some salt to it. Add some salt, and then we'll see if that increases the conductivity. So I'll drop this back into the solution, to the sample. And then I'll start agitating it here. And yeah, you can see over here that our conductivity there of our sample has risen by quite a bit here. So we'll just mix this up a little bit here, agitate it. Actually, maybe move this down a little bit, up and down, and then I'll just let it sit. So yeah, it looks like we get a reading of about 3,200 microsiemens per centimeter for our reading with adding salt. And of course, the more salt we add, the more this should go up. We'll add maybe a little more. So I've added some more. And there you can see our reading over here has gone up already. So we got, for our first measurement, we got 3,200 microsiemens per centimeter. All right, so now that our probe had been exposed to the salt water, I'm just going to lower this. I have since rinsed the probe with deionized water, and I rinsed it twice just to make sure that our reading over here comes back down to a reading that it was when we had deionized water, which was around 4 or 5 microsiemens. So we've got this probe basically cleaned off, because now we're going to measure the conductivity of tap water. All right, so now we're going to do a test with temperature compensation here. So we're going to go ahead and disable temperature compensation. We're going to press menu, go down to program, down to temperature, and we want to set the S1 sensor 1 temperature compensation. We want to set that to manual, and the reference temperature will be 25 degrees C. So there, we've got that set up, and now we're going to take, I've got 2 samples here. I've got tap water here with a at room temperature. I've let it sit in the room for quite a while now, so it's getting close to room temperature. And we're going to see what the conductivity of our tap water is. And let's just drop this back down. So switch that around. It looks like our tap water is has a conductivity of about 439 microsiemens. 439 microsiemens we'll go with. So I'll take this out. And this here was at a temperature, ooh, I forgot to grab the temperature. Let's grab the temperature with that too. So it's around 19. So let's redo these readings here. Around 400, we'll go with 441 and 19 degrees C. 441 and 19 degrees C. So it's pretty close to room temperature, this water. And then now I have some water over here, tap water. And notice how I've kind of put it in an ice bath here, but I separated the two just so our ice didn't interfere with our conductivity measurement. But this water came from the exact same location. It's just at a different temperature. So let's see. Here, I'm going to drop this in. It should be colder. And it looks like we're getting a colder value. It's around 9 degrees. Just let this stabilize. About 300 microsiemens, right about 300 microsiemens, 301. And just wait for our temperature to stabilize. Looks like it's pretty stable there. So we'll go with 300 and 7.7. So now what we're going to do is we're going to compare those same readings with temperature compensation on. So I'm going to go back and enable temperature compensation. So change this from manual to auto. So that's set. All right, so now we were getting different readings at different temperatures. So now let's drop this back in to our cold sample. All right, so our cold sample is now reading approximately 465, so it's quite a bit higher. This could be the result of the temperature compensation. 464 at 7, so go with 465 at 7.5 degrees. I'll grab the other sample, the warmer one. So we're going to drop this one back into the sample that was at about 19 degrees. All right, so we'll just switch this around, let the temperature stabilize. All right, so it's coming up, it's about 18.1. Looks like we may have just the actual cooled probe may have cooled off our sample. It was at 19 before. But there you can see that our readings are a lot closer now, because we're about 460 some at that colder temperature. And we're still up around, we haven't dropped down to 460 yet, but we're about 505, or sorry, 505. We're at 505 at 18.3. So we'll go with 505 at 18.3. So the temperature correction didn't bring it to be both these readings to be the same, but it brought them a lot closer. All right, so we saw that temperature compensation is needed for conductivity measurement. And if you were to actually take, I'll get you guys to do the calculation when we answer our questions, but our percentage change from the two temperatures that we took, our percentage change from the two temperatures divided by the temperature change should equate to approximately that 2% per degree C value. So, but we've seen now with conductivity measurement that temperature compensation is needed, and temperature compensation isn't correct for it exactly, but it definitely does make the two values closer at the two different temperatures. So that is all we have for this video.